All right, let's take a look at our lesson today. So we're going to be working with functions in this unit. And before we jump into some of the more like difference quotient and those kind of things that we're going to do, I want to review functions in general. We just need to kind of dig back into our memories. What does it mean to be a function? So let's look at it graphically. Perhaps we remember from, let's say we have a function that looks like that. And do you remember the graphing test that we used to determine whether it was a function? Do you remember the name? Vertical line test, the vertical line test. So if I draw a vertical line in any place on the graph, I need to touch it one time, and that signifies that it is a function. So in reviewing these, this is important because some of the homework questions that you're going to have are going to ask you whether something is a function or not. Just another graphing example. So if I had an ellipse and I, did my vertical line test, we would see that an ellipse is not a function because it crosses two times. So let's think about it in different terms as well. So instead of just whether it crosses or not, what about input versus output? Do you remember that word, input versus output? So what we're looking at, if we don't have a graph of the relation or function, what we're looking at is our input would be like, let's just pretend that's like x, this location. Let's say that's x equals 3. And so this would be considered our input. To be a function, each input is only allowed one output. If you'll see here, for this case, an output would be like the y value. There are two outputs, which causes this ellipse to not be a function because there are two different outputs for one input. Does that make sense? So we need to think about it in terms of graphing like this, but the homework problems typically won't have a graph. They're going to give you some, points, and they're going to ask you whether it's a function or not. So what we need to keep in mind, to be a function, one input can only equal one output. Okay, you can't have two different outputs for one input. Are we okay and remember that? Everybody's okay with what's a function, how to tell? Okay. So we're going to do some like adding functions together and subtracting, multiplying and dividing. We're going to do all that. We're going to be looking at the domains. This upside down U, just as a reminder, that's a set notation kind of deal. That's called an intersection. Basically, to get the domain of the addition of two functions, we're going to intersect each of their domains. And the intersection means we're going to take all of those that are common. Intersection versus union. Maybe that kind of brings back some memories as well. All right. So that's just a short little recap of functions. Let's look at some more material that perhaps we're not as, maybe we don't know or haven't, probably not. We probably have not talked about or heard about something called a difference quotient. Okay, difference quotient, we're going to be working on difference quotients today. A difference quotient is kind of like slope, to be perfectly honest with you. This h right here, this is the change in x. So if we look at this h right here, we'll look at the change. So this x value used to be like, I don't know, looks like about 0.8. And then it changed, and now the x value is like a 4. So this h represents the change in x. That's what that represents. The denominator represents the change in x. The numerator represents the change in y. So if we look at the numerator, we've got basically this is the new y value, f of x plus h, right here. That's the new y value. And then we have the old y value, which is simply f of x. So the numerator represents the change in y, which if you recall from Algebra 1, the change in y over the change in x is really, we're talking about slope. This is just a more complicated way of dealing with it. So what is the deal with the difference quotient? So the difference quotient is actually part of the derivative. That we're going to be working on derivatives next year. And so let me show you the definition of the derivative. You don't need to memorize this right yet. The limit as h approaches 0 of f of x plus h minus f of x over h. Notice that in this definition of the derivative, this part of it right here is the difference quotient. Okay, that part of the definition of the derivative is, so what we're looking at today is the difference quotient in just the algebraic parts to do with the difference quotient. We're not going to go into limits. That's where we go into calculus. We're just looking at the algebraic portion. And to be perfectly honest with you, the most difficult part in calculus is not the calculus, it's the algebra. And so we're going to be working on the algebra and hopefully to, pave the way to smoother work in calculus. So what is a derivative? So one use of the derivative is the slope of the tangent line. So that is, there's multiple uses of a derivative, but that is the use I'm talking about right now. It's the slope of the tangent line. Okay? So let's look at that in graphing form. Let's look at what that picture looks like. You probably remember what tangent line is from maybe geometry. Remember in geometry when you worked with tangent lines and secant lines? So this is a picture that right here, the green one is the tangent line that has a point of tangency. So what the derivative would tell us would be the slope of that green line. That's what the derivative would tell us. This blue line we would call, this is called a secant line. And the secant line, if you recall from geometry, it cuts through the figure, in this case, like twice. We're just looking at it cutting through the curve 2 times. So I'm going to pause there for just a second. That's that's the conceptual information that we need in order to do what I'm getting ready to show you how to do. I need you to understand what it is that you're doing and finding, okay? The other concept that I want to talk about before we move to the examples is implicit versus explicit form. This is another thing that we use in calculus quite frequently. Let's talk about how we tell them apart. Our norm, what we're used to, is the explicit form of the way that, equations or functions are written, like y equals negative 3x plus 5. That should be kind of normal. That's what we're normally used to. What this is called, it's called the equation, basically we solve the equation for y in terms of x. The words here, this means that y is a function of x. And that's how those are the words that your textbook uses. You're going to have some examples in your homework where it's going to ask you if y is a function of x. What that's really saying, it's kind of code words for, is this written in explicit form, or is the equation written in implicit form? That's what it's asking you. Explicit means y is one of the ways is y is a function of x. Okay, so I know the wording can be very confusing to us, so I want to make sure we completely understand. When you see that in your homework, it's asking you if the equation is written explicitly or implicitly. So implicit, you can see over here, the x's and y's are just jumbled together. Not one is not solved for the other. This would be an implicit form. Okay, that's what that would be. And these are the same equations. They're just written in a different form. On the left, you can see that this equation right here is a line, but it's written with x's and y's all jumbled together. This is also a line, and you can see that the equation is written as a y equals equation. It's just a different way to write an equation. And they have just names. So that's just something I wanted to make sure we're okay with. So this is the same equation right here. That's here. They're just written differently. One is written implicitly, the other is written explicitly. Okay, questions so far? Are we okay? So we've talked about the concepts of difference quotient and how that's like a precursor to calculus. And we've talked about the concept between the way that you write equations, whether you write it explicitly or implicitly. Okay, we all right? Okay, so let's work a few examples. On this first one, we're giving two functions and we're asked to do a few different things. First, we're asked to add these together. So I'm going to actually call this A. This is, 1A and this is 1B. They're asking us to do two different things. They're asking us to add the two functions together, find their domain, and then divide. So let's do that. So we're just going to call this 1A. So if we wanted to do f plus g, we would simply add f, which is 1 over x plus 2, plus g, which is x over x minus 1. Now let's talk about the form that we're going to leave this in when we're adding these together. If these fractions are just regular fractions with a numerator and denominator, and we don't have any other purpose for them, it's not like we're going to solve or do anything else, it's okay if you leave it just like that. If that bothers you and you really want to find a common denominator and add them together, that is perfectly fine as well. That's where you will have a choice. On part B, we won't have a choice, and I will explain the difference. So here, we're just adding the functions together, and we've got to write the domain. So when you're thinking about how to find the domain, what I want you to think of, instead of what are all the values x can be, I want you to think, what are all the values that x can't be? Because we want to eliminate those values, whatever that is. If we're in a fraction form, we know the big danger with fractions, right? We can't have the denominator be 0. So we want to think to ourselves, what values would make the denominator 0? We could actually physically set each denominator equal to 0 and figure that out if we can't just look at it. So in this case, x can't be negative 2 and x can't be 1. So I'm going to write it in set notation first, all x such that x cannot be negative 2 or 1. Your textbook really likes interval notation, so when you're working these problems for homework, it's going to want you to put it in interval notation. So I'm going to write our domain in interval notation also. And we've had a lot of experience with both. So interval notation, we would go from negative infinity to negative 2, then from negative 2 to 1, then from 1 to infinity. So that's the same domain written two different ways. Okay, and your textbook is going to prefer the interval notation way. All right, questions so far? So we've just added two functions together. All right, so now let's divide them. All right, so we'll call this part B. We're going to divide them. They want us to do f divided by g. So f is the 1 over x plus 2, and g is the x over x minus 1. All right. Now, in this instance, this is one where we are not allowed to leave it like that. Let's look at the difference between part A and part B. Part A, we just have two fractions being added together. Part B is a problem because we have fractions inside of fractions. We know that there's not ever okay to leave it like that. You probably remember that from last year. We cannot leave a fraction in complex form. So what we have to do now is we have to rewrite it. Do you remember the whole keep, change, flip from long ago? You remember, right? That keep, change, flip concept. That's how we're going to change this fraction inside of a fraction. We're going to keep the numerator. So let me just write down here. We're going to keep the numerator, so 1 over x plus 2. We're going to change the division to multiplication, and then we're going to flip the denominator, x minus 1 over x. And so that, if you recall, that's how we fix complex fractions. If you can remember that little keep, change, flip thing, that probably will help you. Now, when we're multiplying, hopefully we remember about multiplying fractions. We would multiply the numerators together and the denominators together. That's what we're going to do. So 1 times x minus 1 is just x minus 1. Multiplying the denominator together, I'm actually going to leave it factored. And that's fine. You can multiply it out or you can leave it factored. It's totally up to you. All right, now I want to pause for a second. How are we doing? Okay, so now what we have to do is we have to look at what we have and decide what our domain is. What is our domain? So I'm going to do the same. I'm going to write it in set notation, all x such that. So looking at the denominator, I can see that x can't be 0 and x can't be negative 2. Okay, and if that troubles you, just go to the side. You can say x times x plus 2 equals 0, and you can solve. You can set each one equal to 0, and you can get that way as well, instead of just doing it in your head. So we know all x such that x cannot be negative 2 or 0. And now I'm going to write that in interval notation, because that's what your textbook is going to want. So negative infinity to negative 2, negative 2 to 0, and 0 to infinity. All right, so that's the first kind of problem that you will have homework problems on. Are we okay with that? We know how to add, subtract, divide, all those things, multiply, and find the domain. Okay, perfect. So now we're going to get into now the difference quotient. Okay. So first off, let me write the formula up here for you. So the formula is f of x plus h minus f of x over h. That's the formula for the difference quotient. So the first thing that we need to do is we need to use the difference quotient, the formula, to rewrite what we're doing here. So let's take a look at A. So first up, this is a polynomial. So this is a polynomial. And what I want to do is I really need to explain to you what our end goal is. Because if you don't understand what our end goal is, then this process is going to be difficult. You're going to be like, why? What am I doing? Where am I going? So here's our end goal. Our end goal, the final goal, so we'll put final goal or end goal. Here's our end goal for these problems, these difference quotient problems. Our end goal is to eliminate the single h in the denominator. That doesn't mean that h's can't be in the denominator. I'm talking about this single h right here, that guy that we start out with. The single h needs to be gone. Okay, needs to be gone. That's our goal. So and the way that we do that is going to differ depending on what kind of function we have. So I'm really laying it out here for you specifically. All you need to do is look at the function and then you will be able to figure out how to do this. If it's a polynomial, we're just going to simplify. That's how we take care of polynomials when we're doing difference quotient. So I'm going to pause there for a second. A lot of concepts here. What are we doing? We're trying to get rid of the h. How are we going to do that? In this first instance, we're going to simplify. All right, so let's focus on this x plus h business, this formula. All right, this x plus h, this function, this is function notation, right? What I'm going to do is I'm going to open up every place there's an x in my formula, and I'm going to insert an x plus h. See, everywhere there's an x, think of that as a hole. There's a hole right there, and what we're going to do is we're going to slide into that hole an x plus h. So I have 2 times x plus h squared minus 3 times x plus h. I've just accomplished this f of x plus h business. Okay? I'm just using the formula right now. Minus, and we're going to put a bracket here. I'm going to subtract the function itself, and the function is simply 2x squared minus 3x. And that's all over h. Okay, so I'm going to pause here for a second. All I have done is I have used the formula. I've taken that function and I've applied the formula to it. Any questions so far?
Why did you multiply 3 by 2x squared minus 3x? I mean, sorry, why do you just have the 2x squared minus 3x at the end?
Oh, right, this part right here?
Yes.
This relates to this piece up here. This piece right there, minus the f of x.
Oh, okay.
Yes, ma'am. That's where that comes from. You have to do the f of x plus h, and then you have to subtract the whole function. Other questions? Good questions. You know I love questions. What else do we have? Okay, so I hope you can see why, and possibly relate to why I'm saying the hardest part of calculus is algebra. This is where students in calculus get mixed up, is actually using the formula for the difference quotient and simplifying it. That's all we're going to do. We're using the formula for a difference quotient and we're going to simplify it. All right, so what do we need to do? We need to do algebra. Yay, we love algebra. Okay, I love algebra. Yes. Okay, maybe I have some algebra lovers out there. I don't know. We're going to take this, and I hope that we remember from last year that we can't distribute the 2. We actually have to do order of operations. We're going to have to do the squaring first. We're going to have to multiply that out. Remember that? X times x is x squared. X times h is xh. X times h is xh. H times x is h squared. And so many of you can probably do that in your head. I'm just, writing this. This is how we want to think. And so what we would do is we would say, we're in the process of simplifying, so 2 times, and that's x squared plus 2xh plus h squared. That's what I get for that first little piece, and I'm going to distribute the negative 3, so negative 3x minus negative 3h, and then I'm going to distribute the negative, so negative 2x squared plus 3x. All over h. Now, I just want to let you know, as I always try to, where the most common mistakes are. The most common mistakes for my students in pre-calculus and calculus is to forget that denominator, that little baby h. They're like, oh, yeah, I can get rid of it. I'll just erase it. No, that's not really the way it works. All right, we got to remember to copy it down. Okay, so let's keep working on our simplification. So I'm going to distribute the 2. So I have 2x squared plus 4xh plus 2h squared minus 3x minus 3h minus 2x squared plus 3x all over h. Now when you get to this point, every single time you should have several things that cancel out. If you don't, then you need to understand you've done something wrong. So here we go. So I've got the 2x squared and the minus 2x squared, those go away. Do we see anything else that should go away? Yep, the 3x's, the minus 3x and the plus 3x, those are gone. And so what we're left with is 4xh plus 2h squared minus 3h all over h. Now remember, my final goal, my ultimate goal is to get rid of the h in the bottom, in the denominator. So let's think through, what could I do to the numerator that would help me out? Does anybody see that? What could I do to the numerator that would help me get rid of the h in the denominator? What about factoring an h out? Could I do that? I can, right? Let's factor an h out. I'm left with 4x plus 2h minus 3 all over h. And beautifully, the h's go away, which was what my final goal was. And I'm left with 4x plus 2h minus 3. Okay, I got rid of that single h on the bottom, and that is my goal. When I'm working on these difference quotients, that's what I want to have happen. I want the single h to go away. Okay, so I hope you can see. So if we were in calculus, you would be doing the limit now. The limit as h approaches 0. We're not doing limits yet, but I'm just saying you would need to get through all of that algebra in order to do the calculus, to do the limit. Okay? All right, let me shrink this just a little bit. I don't know about y'all, but I love being able to shrink stuff. I've become so spoiled with shrinking things that when I write on paper, I'm like, wait, I want to shrink it. And I can't. So yes, I'm totally spoiled by this computer. All right. We doing okay? All right, so let's look at the next kind of an equation. This is a radical. And what I'm doing is I'm actually telling you exactly what you need to do depending on which function you have. That's how you're going to tell. There should be no mystery work here. If you have a polynomial, you just need to simplify, multiply everything out, simplify. If you have a radical, what you need to do is you need to multiply by the conjugate. Multiply by, basically it's the conjugate over itself. Multiplying by the number 1, conjugate over conjugate. And we did this last year. You may or may not remember. We're going to dig way back into your memories, ladies. Okay, so conjugate. Do we remember what that vocabulary word means? What is the conjugate? Uh-huh.
Like the negative version?
Yeah, it's like the negative or opposite version, right? If I had, like, we did it with imaginary numbers. We did it with lots of things. But remember last year, imaginary numbers were like, okay, well, if we have 3 plus I, what's the conjugate of 3 plus I? Remember, it's 3 minus I. We would just change the middle sign. Remember that? That's what we're doing here. We're gonna multiply by the conjugate. But let's first put it into our formula. Okay, so let's use our formula first. Let's take a look at it. So we want to do f of x plus h. So I'm going to take this where this x is, and I'm going to open that up, and I'm going to slide in an x plus h, because that's what the function notation is telling me to do. So I just did the f of x plus h business. Then I want to subtract the actual function, which is the square root of x, and then I put it over h. Okay, so that's using my formula. All I did was use my formula. Okay, so now our technique that we're going to use is we're going to multiply by the conjugate. Now let me shrink this just a little bit. Okay, we're going to multiply by the conjugate. And so over itself. So we've got the square root of x plus h plus the square root of x over the square root of x plus h plus the square root of x. Now this should be very freeing for you, because if you can remember, if you've got a radical, what to do, it's going to be the same thing every single time. You're going to multiply by the conjugate over itself. So we're foiling So we do the first times the first, right? Square root of x plus h times the square root of x plus h is just x plus h. And if you recall the beauty of the conjugate, remember the beauty of the conjugate is that when we do the outside and the inside, they go away. So I'm not going to multiply the outside times the inside because they're just going to go away. And then we multiply the last times the last. The square root of x times the square root of x is just x. And then I've got h times the square root of x plus h plus the square root of x. Okay, great. Now remember our ultimate goal, our end goal is to get rid of the h in the denominator, so there must be a way we can do it. So let's see, let's combine like terms. So those x's go away, and I'm left with h over h times the square root of x plus h plus the square root of x. Ah, what's opened up for us, ladies? See how the h's will go away now? Okay, so gone and gone. So my final answer for this one is going to be 1 over the square root of x plus h plus the square root of x. And we accomplished our goal, which was to get rid of the little baby h in the denominator. Okay, how we doing? See, this is not bad, right? Y'all are like, sure, that's not bad. Okay, let's look at our last one. So what this type is called, this is called a rational equation. A rational equation, and what we're going to do here, every time, we're going to simplify the complex fraction. That's how we fix these guys. We simplify, if I could spell, simplify the complex fraction. Okay, that's how we're going to do our end goal, which is getting rid of the h in the bottom. Okay, so let's look at our little formula, f of x plus h. So I'm going to take this location, this x, I'm going to open up that hole, and I'm going to stick in an x plus h. So I have 4 over x plus h minus the function itself, which is 4 over x, all over h. Okay, we got a complex fraction going there, right? We got fractions inside of fractions. So this should dig back to our memory from last year on how we would fix that. So what do we need to do? We need to bring the two fractions in the numerator together. We need to combine them and then do our keep, change, flip business. Okay? So we need a common denominator. All right, we got this. We got this. So that means the 4 over x plus h, we're going to need to multiply that by x over x. And then the 4 over x, we're going to need to multiply that by x plus h over x plus h. Okay. So I'm going to distribute the numerator. So I have 4 times x minus, and then parentheses. Don't forget your parentheses. Then I've got, what do I have? 4x and 4h. All over x times x plus h, all over h. Okay, so let's work on simplifying. So we've got this 4x and the minus 4x are gone. Right, those are gone. And I'm left with a negative 4h over x times x plus h. I'm going to do my keep, change, flip. Okay, I'm keeping that. I'm changing division to multiplication, and I'm flipping the denominator so that I can get my non-complex form. Okay. So again, our goal is to get rid of the single h on the bottom. Can we do that yet? See how that's lining up for us? So that h is going to go with that h, and I'm left with negative 4 over x times x plus h. Again, it's okay to have the x plus h. It's okay to have an h in the denominator. It's just not okay to have that initial h in the denominator. That's what's not okay. Okay?